Chapter 4. In Chapter 4, we start to think of matrices as a set of vectors, and depending on the arrangement of the vectors, we can do different things with them. We start looking at our dot product and calling it an inner product, but our dot product property still holds. So, for example, our Euclidean inner product of u comma v is still equal to v comma u. Our Euclidean norm, which is the same idea as a distance, is still defined as the magnitude of u, and that is still equal to the square root of u dot u. And Euclidean distance is basically the distance between two vectors, so the magnitude of u minus v. And I will show an example with each one of these. Transformations of matrices, these are the four main ones we talked about: reflection, rotation, dilation, and projection. Talked about it in 2 dimensions and 3 dimensions, and then we started generalizing to the idea of linear transformations. We talked about domain, codomain, and range, so I'm going to try to show you visually what we're looking at with each one of those. Basically, I have a transformation T that takes a set of objects to another set of objects. And so this is my mapping T. This here would be the domain, and this here would be the codomain. And typically you see the way a transformation defined is you'll see something like T defined from, let's say, R3 to M 2 by 2. So this would be like a 3-dimensional vector, A, B, C, and the output is a 2 by 2 matrix of some sort, x1, x2, x3, and x4. So R3 is the domain. That is where I'm coming from. M22 is the codomain. That's where I'm going to. Now the range is basically a subset inside the codomain. And I guess to be more specific, T doesn't map to the codomain so much as it does maps to the range. So that's the idea of domain, where codomain is, and where the range is. Now, let's say I took an example of T. Here's my domain, and it maps to a set. And it turns out this set is both the codomain and the range. If this is true, then T, the vector T, is onto, because it maps to everything in the codomain, which is also the range. A third situation, let's say I have my domain and my codomain, and here's my range. And not only do I have a T that maps this way, but I also have a T inverse that goes in the reverse direction. So here's my domain, and here's my range. If this situation holds, then T is 1 to 1, because for every element in the output, I can correspond it to an element in the input. So these are the 3 situations. This is sort of the general one up here. This is the onto idea, and this is the 1-to-1 idea. Alright, so now let's start taking this section by section and looking at different things. First, I wanted to start with the general ideas with vectors. So, U inner product V. Now, one thing we talked about is that I can think of this as 2 matrices. So I could think of this as U transpose V, because I can rewrite this as a row, -7, 1, 3, 2. Transpose it, that's where the row idea comes from, and multiply by the matrix 1, 8, 9, 6. So that would equal -7 plus 8 plus 27 plus 12, which would equal 40. And as you can imagine, since this is basically a dot product, U transpose V should equal V transpose U, which means I should be able to rewrite it the other way. 1, 8, 9, 6, and -7, 1, 3, 2, and get the same thing. So dot product properties, inner product properties should be the same. Distance between u and v is the magnitude of u minus v. So if I subtract my u and v vectors, I'm going to get something like negative 8, negative 7, negative 6, and negative 4. And then to find the magnitude of that, I'm basically going to do the vector dot itself and then square root it. So square root of 64 plus 49 plus 36 plus 16. And I believe this is equal to the square root of 165. Okay, continuing on. Question number 3 was to find if negative 29, negative 7, 29, and 38 is a linear combination of u, v, and w. So basically what that means is I want to find some multiple times u, which is negative 7, 1, 3, 2, plus some scalar multiple times v, which is 1896, plus some scalar times w, 21810. And I want that to equal negative 29, negative 7, 29, and 38. Well, let's take a look at this as components. That would mean I want negative 7a plus b plus 2c to equal negative 27. I would need a plus 8b plus 1c to equal negative 7. 3a plus 9b plus 8c to equal 29. And 2a plus 6b plus 10c to equal 38. However, if I change this to a matrix, that would basically be the same as saying a matrix with negative 7, 1, and 2 in the first row, times the vector a, b, c, has to equal negative 27. And second row would be 1, 8, 1 would equal negative 7. 3, 9, 8 would have to equal 29. And 2, 6, 10 would have to equal 38. But notice, those are exactly my vectors u, v, and w, 1896 and 21810, written as columns. So what that means is a matrix is basically representing a linear combination of its columns. So if I set this up as an augmented matrix, negative 7, 1, 2, negative 27, 1, 8, 1, negative 7, 3, 9, 8, 29, and 2, 6, 10, 38, and then RREF this on my calculator. The result is going to be 1005, 010, negative 2, 0014, and 0000. Now going back to my solutions, that means A equals 5, B equals negative 2, and C equals 4. And so 5u vectors minus 2v plus 4w is equal to the vector that I was interested in, which was negative 29, negative 7, 29, and 38. So that was part C. Part D, question 4 says find the vector orthogonal to u, v, and w. So now what I'm interested in is a vector so that when it dots u, it equals 0. When it dots v, it equals 0. And when it dots w, it equals 0. So this time if I set it up, I'm looking for a vector a, b, c, d such that negative 7a plus b plus 3c plus 2d equals 0. So that comes from the idea of u dot my unknown vector. Let's call it x. And likewise, if I set up the other ones, if I dot it with v, I would get a plus 8b plus 9c plus 6d equals 0. If I set up the last one, I would have 2a plus b plus 8c plus 10d equals 0. So this would be v dot my vector x, and this would be w dot my vector x. But again, I can rewrite this as a matrix. So the matrix for this would be the following. It would be negative 7, 1, 3, 2. And this time I want A, B, C, D going this way. And I want that first one to equal 0. And then the next one would be 1, 8, 9, 6, 0. And 2, 1, 8, 10, 0. But notice this time, my U, my V, and my W are written in rows. So if I want to take a dot product between vectors, I want to set up the matrix with row vectors. And if I want to take a linear combination, I want to set up my matrix with column vectors. So setting this up as an augmented, negative 7, 1, 3, 2, and 0. 1, 8, 9, 6, and 0. 2, 1, 8, 10, and 0. And same thing, I'll do an RREF on this. Hopefully I did it correctly. I got 1, 0, 0, 1, 6, 0, 0, 1, 0, negative 11 over 15, 0, and 0, 0, 1, 13 over 10. 0. So if I translate this back into A, B, C, D, this means that A plus 1/6D equals 0, B minus 11/15 D equals 0, and C plus 13/10 D equals 0. So that means that A equals negative 1/6 D, B equals 11/15 D, and C equals negative 13/10 D. And then setting up my solution for this, that means my vector A, B, C, D would equal negative 1/6 D, 11/15 D, negative 13/10 D, and D. And if I factor out the D, I'm looking at negative 1/6, 11/15, negative 13/10, and 1. So this is my answer. And any scalar multiple of that vector should also be orthogonal, so that's why there's D there, and hence that's why there's infinite solutions. Now let's look at just using properties to answer some certain questions. So I know the magnitude of U equals 3, the magnitude of V is 4, and I know the Euclidean inner product between U and V equals 15. And I need to find the magnitude of U plus V. However, I'm going to say stop and talk about one other property we looked at, which was the Cauchy-Schwarz inequality. The Cauchy-Schwarz inequality says the absolute value of the inner product of U and V is always less than or equal to magnitude of U times the magnitude of V. But if I look at this here, I get 15 is less than or equal to 3 times 4. So this is impossible because it doesn't satisfy Cauchy-Schwarz. So I'm going to rewrite it. Let's change this to 15. And let's change this to 4. Now, that's actually going to work. Okay, because now if I do inner product of U and V, I get 4 is less than or equal to 3 times 15. Much better. So let's look at U plus V. magnitude. Well, if I square that, that equals u plus v, inner product u plus v. And since inner products are distributive, this is the same as u inner product u plus u inner product v plus v inner product u plus v inner product v. And u inner product u is magnitude of u squared. U dot v and v dot u are equal to each other, so that's 2 times the magnitude, or 2 times u dot v plus the magnitude of v squared. So magnitude of u squared is 3 squared plus 2 times my new u dot v, which is 4, plus 15 squared. And all that equals 242. So then the magnitude of u plus v equals the square root of 242. I notice I didn't need to know any of the components of u and v to put that together. However, I did need to make sure Cauchy-Schwarz worked. So speaking of Cauchy-Schwarz, I know in this unit we had several Cauchy-Schwarz proofs, and I wanted to show you an example of how to put a Cauchy-Schwarz proof together. The way you want to recognize it's a Cauchy-Schwarz is if you see that inequality sign, then that's the idea that you're going to take two vectors and basically apply the Cauchy-Schwarz theorem to it. So what we have to do here is figure out what to use as our two vectors and then apply the Cauchy-Schwarz. Let's say we let u equal a and b. Since I've got that 1/2 there, I'm going to let v equal 1/2, comma 1/2. So Cauchy-Schwarz says that the magnitude of u dot v is less than or equal to the magnitude of u times the magnitude of v. If I square both sides, that means u dot v squared is less than or equal to the magnitude of u squared plus the magnitude, times the magnitude of v squared. But if I take these two vectors that I have here, u dot v is going to be a over 2 plus b over 2 squared, less than or equal to the magnitude of a squared, which is a squared plus b squared, and the magnitude of v squared, which is 1/4 plus 1/4. So, rewriting both sides, I get a plus b over 2 squared is less than or equal to a squared plus b squared over 2. And we're done. Section 2 of Chapter 4, we looked at transformations. What I suggested was to build it one transformation at a time and just make sure you do it in the correct order. So basically, we want to think of it as I have a vector x. I'm applying a transformation to that. To that result, I'm applying another transformation. To that result, I'm applying another transformation. So as you're building these transformations, you want to start from the right and build towards the left. We have here 3 transformations. Rotation 30 degrees about the x-axis, followed by 45 degrees about the y-axis, followed by reflection about the xz plane. So I will do these one at a time. Let's start with the rotation of 30 degrees about the x-axis. So if I were to draw a picture, here's my x-axis, here's my y, here's my z. If I rotate a vector about the x-axis, anything on the x-axis stays on itself. So my first column is going to stay 1, 0, 0. If I take the y vector, or something along the y-axis, which would be 0, 1, 0, and rotate it 30 degrees about with respect to the x-axis, I'm going to end up here, and this is cosine 30, sine 30. And if I take my z vector 0, 0, 1 and rotate it, I'm going to end up at negative sine 30 and cosine 30. So my second column is going to be 0, cosine 30, sine 30, and then 0, negative sine 30, cosine 30. So that's the first one. The next one, rotation of 45 degrees about the y-axis. So as you can imagine, the y column stays the same, and I only want to focus on the x and the z. Now this is where you have to be a little bit careful. So if here is my y component, if you think about the orientation we normally have, our positive x is actually going this way now, and our positive z is actually going this way. So imagine taking this drawing over here. Oops, taking this drawing here. And now imagine the y coming straight out at you. So now what this means is if I take a vector along the x-axis, if I rotate it 45 degrees, what happens is I'm going to have a positive x value, and I'm going to have a negative z value. So I have cosine of 45 here, 0, and now negative sine of 45 here. If I take a vector in the z direction and rotate it 45 degrees, the result is going to be a positive x and a positive z value. So this is sine of 45, 0, cosine of 45. So those get multiplied. And then the last one is my reflection about the xz plane. So here's my x, y, z. And here's my xz plane. So if I reflect anything on the x-axis, along the xz plane, it stays where it is. So the first column is 1, 0, 0. Anything along the y-axis, though, gets reflected to its opposite. So that's going to be 0, negative 1, 0. And anything in the z-axis gets reflected to itself. So that's 0, 0, 1. And you multiply all three together, and that would be a single matrix representing all three transformations at the same time. That is a very colorful slide. Now, we also talked about how to build it algebraically, so that's what I'm going to do here. I'm going to do something in R2, and we're going to basically create a matrix to represent reflection over the line y equals negative 1/3 x. So kind of like the other one that I just did, except to create the columns in the matrix is going to be a little bit more involved because the line isn't like one of the orthogonal axes. So we're going to start by taking the point 1, 0, reflect it over the y equals negative 1/3, and I typically call it like A and B. So 1, 0 gets reflected to A, comma B. And now we want to look at the properties of reflection to help solve for A and B. For example, I know the slope here would have to be 3. So that means B minus 0 over A minus 1 has to equal 3. I also know the midpoint has to be on the line. So the midpoint would be A plus 1 over 2 and B over 2. And that has to be on my line, y equals negative 1/3 x. So that means B over 2 has to equal negative 1/3 A plus 1 over 2. So if I take these two, it's a system of equations, and solve, I get A equals 4/5 and B equals negative 3/5. So in my matrix T, my first column is going to be 4/5 and negative 3/5. Now I'm going to do the same with the other point. So if I take 0, 1 and reflect it, it's going to end up somewhere down here. So I will call that CD. So 0, 1 maps to CD. Same idea. Slope, D minus 1 over C has to equal 3. And the midpoint, D plus 1 over 2 has to equal negative 1/3 times C over 2. So if I solve these two here, I get D equals negative 4/5, and I get C equals negative 3/5. So my second column, which is what happens to 0, 1, is going to be negative 3/5, and this is negative 4/5. So again, the way a matrix is built, this is what happens to my first basis vector, which would be 1, comma 0. This is what happens to my second basis vector, which is 0, comma 1. And this is my final answer. Alright, let's practice from section 3 now, the whole idea of domain, codomain, and range. So what you want to think of for domain and codomain is what do I multiply by and what is the result. Given A here, if that is my mapping, I would have 1, 2, negative 1, 4, 5, 2, 1, 3, 0, 3, 2, 2. And we'll stick with vectors in this example. So the vector I would multiply this by would have to have 4 components, x1, x2, x3, and x4. And if I were to multiply this matrix times that vector, I would get b1, b2, and b3. So just from that, I know that the domain would have to be a vector with 4 components to it. So the domain would be R4. The codomain would have to be a vector with 3 components in it, so the codomain is R3. There, 2 of the 3 figured out. Now what I have to do is figure out the range. So to figure out the range, I need to know what values of B1, B2, and B3 actually get mapped to. To do that, I'm going to set this up as an augmented matrix. 1, 4, 5, 2, 2, 1, 3, 0. Negative 1, three, 2, 2, and I'm going to augment it with B1, B2, and B3. So I'm going to go through my boring row operations here. I'm going to do row 2 minus 2 row 1s, and I'm going to do row 3 plus row 1. So if I do 1, 4, 5, 2, B sub 1, row 2 minus 2 row 1s is going to be 0, negative 7, 3 minus 10 is negative 7, 0 minus 4 is negative 4. And that is B2 minus 2B1. And then, let's see, row 3 plus row 1, 0, 7, 7, 4. So that's B3 plus B1. I'm going to do one more row operation here. So we're going to do row 3 plus row 2. Because we notice if I do row 3 plus row 2, that last row cancels out. So I'm going to have 0, 7, 7, 4, just because I don't like negatives. And then this will be 0, 0, 0, 0. And I get B3 plus B1 plus B2 minus 2B1. Now the whole idea here is I want this to be a consistent system, which means that it has a solution. And if it has a solution, then B3 plus B1 plus B2 minus 2B1, this last component there, has to equal 0. If it equaled anything else, that would mean no solution as a result. So now it means that B3 has to equal, I feel like I did something wrong. B3 has to equal, I'm pausing here. Row 3 plus row 2 has to equal B1 minus B2. Let me check that. So if I go up here, this means that B3 plus B1 basically has to equal the opposite, 2B1 minus B2. So B3 equals B1 minus B2. Okay, we're good. Okay, so B3 has to equal B1 minus B2. Well, what that means is not every B3 element is defined. And in fact, if I were to look at my range of values, B1, B2, and B3, since B3 equals B1 minus B2, I could rewrite this as B1, B2, and b1 minus b2, which would be a linear combination of 1, 0, 1 times b1 plus 0 to negative 1 times b2. But this does not represent 3 dimensions. It only represents 2 dimensions, a plane. Because 2 vectors only represent a plane, they can't represent 3 dimensions. So let's finish this up. That means our range is R2. That means that A is not on 2 because not all of the codomain can be mapped to by A. So then my last thing I have to figure out is 1-to-1. Alright, so let's do that. So going back to my RREF, 14520774. Let me write it down here. 14520774. And the result is I have B1, I have B2 minus 2B1. And then this is my row of zeros. So if I were to try to solve for this, this would mean that x1 plus 4x2 plus 5x3 plus 2x4 equals b1. And it would mean that 7x2 plus 7x3 plus 4x4 equals b2. But there are not enough equations to solve for x1, x2, x3, x4 in terms of b1 and b2. Therefore, A is not 1-to-1. To be 1-to-1, I need to be able to find an inverse function, or I need to show that every element can be mapped to a unique element in the domain. Since I cannot define an inverse function, meaning I can't solve for x1, x2, x3, and x4 in terms of b1 and b2, it is not 1-to-1. Now I want to continue practicing the idea of 1-to-1 onto, and also look at linear transformations as we go through this. So we're going to do these one at a time. Let's start with our first one. Now, to be a linear transformation means that 2 properties have to hold. T of u plus v has to equal T of u plus T of v. So I'm going to start with that. In this case, let's say u equals my vectors u1, u2, u3. And v, let's define it as v1, v2, and v3. Then u plus v would equal u1 plus v1, u2 plus v2, u3 plus v3. And consequently, T of u plus v would equal u1 plus v1 plus 1, because it's my x component, plus 1, u2 plus v2 minus 2, and u3 plus v3. Now if I look at this individually, T of u equals u1 plus 1, u2 minus 2, and u3. T of v equals v1 plus 1, v2 minus 2, and v3. And so if I were to add them individually, I would get T of u plus T of v to equal u1 plus v1 plus 2, u2 minus v2, plus v2 minus 4, and u3 plus v3. But notice that means that T of u plus v is not equal to T of u plus T of v. So this is not linear. Oh, I wanted to do more. Alright, let's take a look at the idea of onto. If I go back to my definition for t, I had t of xyz equals x plus 1, y minus 2, and z. So the domain is R3. The codomain is R3. But technically adding 1 and negative 2 to the x and y component, I can still get everything in R3 for the output, so the range is also R3. And since these two are equal, T is onto. Alright, then let's check the last one. Is it 1-to-1? Well, can I define an inverse function? So let's say this. Let's say T of x, y, z equals a, b, c, where a equals x plus 1, b equals y minus 2, and c equals z. So can I go backwards? Can I solve for x in terms of a, b's, and c's? So x would equal a minus 1, y would equal b plus 2, and z would equal c. So that means T inverse exists. And so this is 1-to-1. Okay, we'll go through the same idea then with each of these. Let's start with this one. Well, let's start with the whole idea of linear. So we'll do the same thing. T of u would equal then the x and the y component. So that would be, actually, let's do this. No, I like that. Okay. So T of u would equal, basically, u1, u2, because it's the x and the y component of u, comma, u1 times u3. And T of v would equal v1, v2, comma, v1, v3. And so therefore, oh, actually, I wanted to use the other one. Let's do the scalar one instead. So there's T of u. So then T of ku would basically equal T of ku1, comma, ku2, comma, ku3. Because k is a scalar being multiplied by the vector u. And so if I apply t to this, I'm going to get the x and the y component multiplied together. So that's going to be k squared u1, u2. And then the x and the z component multiplied together, so that would be this times this. So that's going to be k squared u1, u3. But if I were to do k times t of u, using this one here, I would get k times u1, u2, comma, u1, u3, which would equal k u1, u2, and k u1, u3. But if we look at these two, t of ku is not equal to k of t of u, and so this is not linear. Okay, then let's take a look at the others. Onto. So t goes from R3 to R2. And everything can basically be mapped onto. So this is on, so t is onto, because I can define every possible matrix, or every possible element in R2 with x, y, and xz, depending on what x, y, and z are. Is it 1-to-1? Well, I want to show that one solution could actually come from two different vectors. So let's see. So let's make up an example. Let's say I had t of x, y, z equal to something like 3 and 9. The question is, could I have a single value of x, y, z that would map to 3 and 9? Well, this would mean that x times y equals 3 and x times z equals 9. So for example, a possible solution would be something like x equals 3, y equals 1, and z equals 3, because x times y is 3 and x times z equals 9. However, I could also have something like x equals 2, which would mean y equals 3 halves, and z equals 9 halves. So since one output generates more than one input, this is not 1-to-1. And my last example with these. So this one, I'm going from M33 to R3. M33 basically means 3 by 3 matrices. And so all this transformation is going to do is create a vector basically out of the diagonal elements. For example, let's say I had t of something like, I don't know, 1, 2, 3, 4, 7, 6, 9, -5, and 6. And what this is going to do is create a vector out of just the diagonal elements. So 1, 7, 8. So let's start with the idea of linear. Is t of a plus b equal to t of a plus t of b? Well, t of a plus b would basically be something like a11 plus b11, a22 plus b22, and a33 plus b33. So that's t of a plus b. But this is equal to a11, comma a22, comma a33, plus b11, b22, b33, which is equal to t of a plus t of b. So that checks. Now let's check the other one. So we're saying t of k times a. So that would basically be each diagonal element gets multiplied by k, and the result would then be k of a11, k of a22, k of a33. And I could factor out the k, then this would equal k of a11, a22, a33, which is k of t of a. So t is linear. Let's check the rest. So, just to recall, t of a equals a11, a22, a33. No restrictions on the diagonal elements, so T is onto, because any R3 vector can be created depending on how A is defined. T is not one-to-one because two different matrices could have the same diagonal elements. So hopefully that gives you an idea of how to find onto, one-to-one, and to justify if something is linear. Now let's talk about eigenvalues and eigenvectors. And we did these very visually rather than using the matrix to help them out. So the first one is the projection onto the plane 2x minus 3y plus 5z. So if I were to draw a picture, here's my plane. I know that anything on the plane is going to project to itself, and anything perpendicular to the plane is going to project down to the 0 vector. So let's start with perpendicular. Perpendicular would be my normal vector. So n equals 2, negative 3, and 5. Projects to the 0 vector, so lambda equals 0. Now, to find two vectors on the plane, I need a couple of points. So on the plane, let's find some points that satisfy being on the plane. For example, 0, 0, 0, 3, 2, 0, and how about 5, negative 2, 0. 5, negative 2, 0. So if I use these points, I can create a couple of vectors. 3, 2, 0. And let's say take these. That would be negative 2, 4, and 0. So those could be my eigenvalues. This eigenvalue has a lambda equal to 0. These two eigenvectors, would have an eigenvalue of 1 because the vectors would project onto themselves. Let's do something similar to that. So now my mapping is going to project u onto the vector 5, negative 2. So imagine here's my vector 5, negative 2. And here's my u vector. And basically what t is going to do is project u onto 5, negative 2. So again, if it's perpendicular, so perpendicular in this case is going to be the vector 2, 5. 2, 5 is going to project onto 0. So its lambda is going to equal 0. And then anything on the vector, 5, negative 2, will project onto itself. So its lambda is going to equal 1. So this is on the vector itself. And so those would be my eigenvalues and eigenvectors. Now, if you feel really uncomfortable doing it visually, you can always set up the matrix, as you know how to set the transformation matrix up. Do the characteristic equation and find the eigenvalues and eigenvectors that way. That was it. Good luck studying, everyone. Test is on Thursday. Feel free to see me before school or after school this week if you have any questions.